Application of optical isolated probe in double pulse testing. We connected the MikSig optical isolated probe, Tektronix optical isolated probe, and Tektronix differential probe to the driving voltage VG. Use Rogowski coil to measure the IC current. Output voltage is 800 volt. Channel 4 is Tektronix differential probe. Channel 7 is Tektronix optical isolated probe. Channel 8 is MikSig optical isolated probe. Channel 5 is the Rogowski coil current probe. Let's take a closer look at the turn-on process of the second pulse VG. We can see both Tektronix and MikSig optical isolated probes give exactly the same measurement results. Tektronix differential probe shows bigger results. Now let's take a look at the shundown process of the first pulse VG. We can see that Tektronix optical isolated probe and MikSig optical isolated probe still show the identical results, but the differential probe is obviously affected by common mode interference. Let's connect the differential probe to channel 6 with VS to verify this. As we can see, the differential probe's common mode rejection capability is weak and is affected by common mode interference. Now let's check the second pulse's VG turn-on process. We can see the interference on the differential probe. In this double pulse testing case, we can see that optical isolated probes have very high common mode rejection ratio and are not affected by common mode interference at high frequencies and large common mode voltages. Differential probes, on the other hand, cannot suppress common mode interference, which leads to distorted measurements. In double pulse testing of third-generation semiconductors such as silicon carbide and gallium nitride, where the signal rise and fall times are shorter, the advantages of optical isolated probes will be even more obvious.